All right, let's take a look at a new take on molecular orbital theory and ozone. So this is my take on it, which you're not going to find anywhere else. For ozone, you have 3 atoms. They're all oxygens. And you have 8 electrons per oxygen times 3, which means you have 24 electrons total. So for these 3 oxygens, you're going to have a 1s orbital on each, a 2s orbital on each, and each one is going to have 3 2p orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9 total. Now remember the principles of molecular orbital theory that the number of molecular orbitals you get equal the number of atomic orbitals. You get one higher level bonding orbital, or higher level anti-bonding orbital, and one lower level bonding orbital. And you feel like Hund's rule, and you want to make MOs out of similarly energy atomic orbitals. So here I'm going to take these 3 1s's, one from each oxygen, and I'm going to make molecular orbitals out of them. Now, something that we haven't talked about before is this, that you're going to get 3 orbitals. One's going to be anti-bonding, one's going to be bonding, and one's going to be non-bonding. So when you're making MOs out of 3 orbitals, you're going to get 3 like this. And the non-bonding is in between the bonding and the anti-bonding. So these are all going to be the 1s's. You're going to do the same thing for the 2s's. So this one's the anti-bonding, this one's the non-bonding, and this one is the bonding. Now notice the bonding is the most stable out of the 3. Now, what about these guys here? Well, you're going to have a px for each one. You're going to have a py for each one. And you're going to have a pz for each one. So I kind of envision this happening. The x's, of course, make orbitals with the x's, and the y's make orbitals with the y's. But probably something along the lines happens with this. You'll probably get I'm going to call this a sigma, and a sigma. So this is a 2p, a 2p, and a 2p star. So this is going to be an anti, this is going to be a non, and this is going to be a bonding. And you're going to get the same over here. Sigma 2p star, sigma 2p, and a sigma 2p. Non, bonding, and anti-bonding. Now, 3 of these are going to combine to make pi orbitals. Now, the pi orbitals are not going to be as stable as these, so I imagine that they're going to look like this. This is a pi 2p, this is a pi 2p, this is a non, and this is a bonding, and you've got a pi 2p star. So let's put our 24 electrons in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So those are our 24 electrons. Now here, you're going to have a net 0 bonds because the anti-bonding cancels the bonding. Here you're going to have net 0 bonds because the anti-bonding cancel the bonding, and non-bonding don't create a bond. So what are you going to have here? Well, here you have a non-bonding sigma bond, and here you have a bonding sigma bond. So this represents 1 sigma bond. And this also represents 1 sigma bond. And this represents 1 pi bond. So between these 3 atoms, and here these represent no bonds. So between these 3 atoms, you have a net of 2 sigma bonds and 1 pi bond. So if you take a look at that, that's 3 bonds total, and then 3 bonds divided by 2 sets of 3 bonds total by 2 events, if you will, and you got a 1.5 bond order. So that may be one way to look at how this works. It may be that instead we could just turn these all into, if you want, we could turn these all into sigmas and just, blow off or turn these all into pi's and just blow off the sigmas altogether. And you're still going to end up with a 1.5 bond order. All right, that's it. Thanks for listening.